Hey guys, welcome back to Physics with Mrs. Whiteley. Last class we learned about velocity and how it is changing position over time, and we learned how to calculate it with some math. Today we're going to be learning how to represent it using graphing. Okay, so graphing is really nice because it will allow us to visualize motion a little bit better. You can figure out the numbers with calculation, but as far as visualizing what actually happens, graphing is usually a bit better. So first off, let's go through a few vocabulary words that we learned last time that we need to have on our brains today for position versus time. The first one is position. We actually didn't talk about this one explicitly, okay? Position is simply where an object is located. I'll write that here, where an object is located. And we can say that like X marks the spot because this is represented as an X. And we talked about last time that's because we're going to be looking at horizontal things like on an X-axis in math. Okay, so the position on that axis, the position horizontally, is called the X. And now displacement is a change in position. And we said that change is represented by this Greek letter delta. So the delta means change, position is X. So your displacement is simply how much your X value or your position changes. We also had change in time, which is a delta for change and a T for time, same as last class. And then our last thing was velocity, which was a vector, meaning it had a magnitude or a numerical size and a direction. Okay, so we've got all of those things. They are the same as last class. So we're going to look at motion along a number line, okay? Because everything we're doing is horizontal, one-dimensional. Now, a number line has to have numbers. That's kind of the point of it. And we really don't care what the numbers are. I'm not going to label all of them right here. But the important one is having a 0 point, okay? So when we're looking at motion, there are going to be some things that we have to arbitrarily choose. That means we just have to pick something and stick with it. And what we're going to do here is pick a place that we call 0. We're going to stick to it. That place is called the origin. Okay, just like on an XY graph, the origin is right in the middle. Same idea. We're choosing a place to mark as 0 and we're calling it the origin. Okay, so if, for example, I was going to be calculating my displacement from here in Hallsville to Shreveport or to Dallas or whatever, I would probably call Hallsville, my starting point, my origin. Okay, that's 0 miles away is my origin here in Hallsville. So I'm just choosing a place to mark as my 0 point. And then the other thing we're going to have to choose for our number line is directions. So when we're dealing with velocity and displacement, those are vector quantities, which we learned about last time, and vectors have to have direction. And in order to mathematically deal with direction, we're going to stop using up, down, left, right, east, west, north, south, all that kind of stuff, and we're going to start using positives and negatives. So these two blanks here, we're going to decide on our number line which direction is positive and which direction is negative. In most cases in math, the convention is that we always put positive on the right side and negative on the left side. You can actually do it opposite of that and it'd be perfectly fine. You just need to choose in your question, in your problem, when you're looking at motion, which direction you want to be positive and which direction you want to be negative. Right now, I'm going to say right is positive and left is negative. Okay, so we're going to look at some examples down here using these positives and negatives. And the sentence here says, when we use vectors, we'll use positive and negative to indicate direction. And our example is finding the displacement for each of the following examples. So let's look at number 1 here. We've got a number line. 0 is going to be right there in the middle. That's our origin. Our place that we're marking is 0. And we are going to need to pick a positive and a negative. I'm going to go with convention here. call the right side positive and the left side negative. Okay, so what's happening here is we're starting at this point. Okay, so I need to know the numerical value for that position. Since this side is negative, we'll go -1, -2, -3, -4. So I'm starting off here at -4, and then I move all the way over following the arrow to this point, which is 1, 2, 3, 4. So I move from -4 to 4. Now what I'm trying to find is my displacement, how much my x changed. In order to figure out how much it changed, I just need to see how many spaces it went over. It was 1, 2, 3, 4, 5, 6, 7, 8. I moved 8 spaces over. But since I need a vector, okay, something that indicates direction, instead of saying 8 to the right, now I'm going to say it's 8 in the positive direction. So that is a positive 8. You don't actually have to write the positive, it's implied, but I'm going to put it there so you know what I'm talking about. So this is just saying we moved 8 spaces in the positive direction. Let's look at that again, but down here with number 2. Okay, so number 2 has, I'm going to go ahead and label my numbers again as far as I need to. This one doesn't have a direction set yet. I'm going to make right positive again and left negative. And I'm going to start here at the tail end of my arrow at 1. Okay, I'm starting at 1. And then I am moving all the way over to -3. Start at 1, end up at -3. Now what I need to know is how much my position changes. As a numerical quantity, we're moving over 1, 2, 3, 4. So I'm going over 4, which is the length of how far I have moved. But this time, I'm moving to the left. Okay, so instead of writing left, to mean the same thing, I'm going to say I'm going in the negative direction. So I'm going to make this a -4. My change in position is negative this time because I'm going left in the negative direction. Now let's try that again with number 3. Now number 3 is a little bit gnarly, okay? And the reason is because we got 2 arrows here, all right? We're starting at -1, -2, -3, -4. We're starting at -5. And we're going to go all the way over here to 1, 2, 3, 4, +4, if I'm keeping my same sign conventions, okay? And that is moving 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces over. And that's in the positive direction. So my first arrow goes a +9, but then I backpedal, okay? I'm going back the other direction, starting at 4 and going back to 1. I end up going 1, 2, 3 in the other direction. And that's a -3 because I'm going to the left in the negative direction. So overall, if I look at where I started, right here, to where I ended, my total displacement, my total change in position is from -5 to 1. That's moving over 1, 2, 3, 4, 5, 6 in the positive direction. So what's happened here is I went +9 and then I went -3. If you add those together, +9 and -3, you end up with this +6, which tells you where I actually ended up. I ended up 6 away from my starting point and in the positive direction. So my displacement is a +6. All right, so now we're going to take that idea that we just learned of moving in the positive direction, in the negative direction, along the number line, and we're going to apply that to a thing called a position time graph. So with the number lines, we were only looking at position, only the x. But now we're going to start looking at how that position changes with time. Okay, so time ends up on our horizontal axis, and the position ends up on our vertical axis. I'm not going to call them x and y anymore because we're not really going to have x and y on the horizontal and vertical respectively. So I'm just going to call them horizontal and vertical instead of x and y. So over here horizontally, we're looking at time. as I move along the horizontal axis, as I move along here, that means my time is getting bigger. And then as I move up, as I move along this vertical axis, that means my x, or horizontal position, is changing. Okay. So if you look at this graph, there's a few things we need to check out. So if you look at time equals 0, okay, where time is 0 is right here at the beginning. Okay, at time equals 0, where is my graph? My graph is down here at -6. So if I was looking at this motion on a number line, I would be starting off my position at -6. And I'm going to go ahead and draw that here. All right, so at the beginning, at time equals 0, I'm starting at -6 on my number line right here. And then as the graph moves through the numbers here, okay, as time passes, my x value starts changing. It starts going up. That means I am moving. And as it goes up, we end up where time is 3.5 seconds. We end up at position 8. So we're starting off at 6, and we are moving over 3.5 seconds all the way to 8. That's all this means. We're starting at 6, and then we're moving to 8. That's this first section of the graph. Okay, we start at -6 and move up to 8. And then during the next section, we go from that 8 where we were to 9, but it takes us longer. Okay, it takes from 3.5 seconds to 6 seconds. So if we're going a short distance from 8 to 9 over the same period of time, that means we're going to be moving a lot slower. And then here at 6 seconds, our graph flatlines. When it flatlines, that means that it's staying on this same x position that whole time. So from 6 seconds to 8 seconds, all I'm doing is chilling there on the 9, which means I'm not moving. And then over here, this last section, I'm starting at 9, and over those last 6 seconds, I'm going to be moving towards 0. So I start here at 9, and I move back towards 0. So if you follow this whole graph over time, I'm starting at -6, I'm moving at a pretty good pace towards 8, and then I go really slow to 9, then I chill for a bit, and then I move back to 0. So you can simply follow the graph to figure out what is happening with the motion. Now the next thing we need to talk about with the position time graph is the slope. I need to zoom out a little bit so we can see it here. All right, so slope you learned about way back in algebra. And the thing you probably learned about slope is that it is equal to rise over run. Okay, and that's a phrase you've heard plenty of times. Slope equals rise over run. So let's look at this graph and see what rise over run means. I'm going to go ahead and erase all my annotations here so that I can go again. All right, so if we're looking at this first section, okay, this first straight line, we're going to take one straight line at a time. And we calculate the rise, okay, that is going all the way from here up to 8, okay? Simply how much it goes up is the rise. And from -6 to 8, if you count it or do the math, is 14, okay? But as a variable, what we're looking at there is going from an x of -6 to an x of 8. So the thing changing in our rise is the x. So that's a change in x. And then if we look at the run, as we go over, that's from 1 to 3.5 seconds. So that's a 3.5. As we go over horizontally, the thing that's changing isn't our x. We're staying on x equals 8. The thing that's changing is our time. So we'll have a delta t change in time. And we learned yesterday that delta x divided by delta t is a wonderful thing called velocity. So what you get from this is that the slope of your graph equals the velocity. okay? Slope equals velocity for the position time graph. That's the big thing to take away here. And there's some things you need to know based on this. If something has a steep slope, okay, steep slope, which would look like this on a graph, steep slope is a high number slope. That means fast, okay? For example, if we take the rise over run of this that we just did, the rise was 14, the run is 3.5. When you divide those things, you get a slope of 4 equals 4. Okay, so your velocity there for this first section is 4 meters per second. But if you look at this next little section, okay, the rise on the next section is just 1. Okay, I'm going to calculate that here. Rise is 1. And your run is actually 5 spaces over, but each space down here is a half second. So it rises 1 and it goes over 2.5 seconds. So if you do 1 divided by 2.5, the number you will get is 0.4. So that section right there is going to have a velocity of 0.4 meters per second. So a steep slope is going to be fast and a flatter slope is going to be slow. Now if we look at this section right here where it's completely flat, that means it's staying on 9 the whole time. So a flat slope means that it is stopped. Now the other options you have here are you can have a positive slope or a negative slope. You know in math that a positive slope looks like this and a negative slope looks like that. Okay? Positive slope is up and to the right and negative slope is down and to the right. So you can have the same thing with a velocity. You can have a positive velocity or you can have a negative velocity. And all this means is which direction you're going. If you remember our number line, positive was to the right, negative was to the left. So if you have a positive velocity number, it means you're moving to the right. If you have a negative velocity number, it means you're moving to the left. So from a position time graph, you can find velocity, you can tell which direction an object is going, positive or negative, which is right or left. And you can tell if the speed is fast, slow, or if it is stopped. So let's take that knowledge and apply it down here to this last section of our notes. Okay, we're going to draw a graph for each of the following scenarios, starting with constant positive velocity. Now all of these are going to be position versus time graphs, same as we were doing, x versus t. And the first one asks for constant positive velocity. Constant means it stays the same the whole time, the slope is not changing. And if the slope is not changing, that simply means it's going to be a straight line. Okay, so constant means straight. And when we say constant positive velocity, that means constant positive slope, since slope is equal to velocity. So our constant positive velocity is going to be a straight line. Positive means it's going up and to the right, and velocity means that's the slope. Okay, so it's simply going to look like this. And it could really start anywhere. You could have a line down here, and it'd be constant positive velocity. You could have one up here, and be a constant positive velocity. All that means is there needs to be a slope that is positive, and you have a straight line. Okay, our next one down here is constant negative velocity. So constant means straight. Velocity is talking about the slope. So we're going to have a constant negative slope. So it's going to look like this. Straight line, going down, and that's the whole shebang. Next up, we've got a still object. Okay, if something is still, that means its position is not changing. If its position is not changing, it's a flat line. Okay, I pick a position in the beginning and I stay there. And these next two are a little bit trickier. We've got an object speeding up, which means our velocity is no longer constant. We said constant is a straight line. But now we're not going to have a straight line. If we're speeding up, we're getting faster. If we're getting faster, that means we're getting steeper, okay? So let's think about it. If we start slow, it looks like this. And then if we get faster, and then faster, and then faster, it starts looking like that, which is a curve. And if your curve is getting steeper, that means you're speeding up. If a curve is getting steeper, that means you are speeding up. But there are actually two options here. You can speed up going positive, but you can also speed up going negative, okay? So if you look at this graph here, it starts off being kind of flat and ends up being pretty steep. Going flat to steep is speeding up. And then if we go look at slowing down, it's going to be the exact opposite of that. If you're slowing down, you start off pretty fast, okay? So that would be something like this. Starting off pretty fast, and then we're going to end up going flatter like that. It's also possible to do that in the negative direction, starting off steep and ending up flat. So if we go steep to flat, that is slowing down. Steep to flat is slowing down. All right, that's all I've got for you today on notes. You have a practice in Google Classroom that is drawing some of these graphs and then doing some stuff with some slope. Complete that and email me if you have any questions. You should have done a velocity quiz today, so make sure you get that turned in. All right, y'all have a good day.